Okay, since part of the material for quiz 2 was covered on this kind of improvised video session that you had to look at, I thought just to be sure it would make sense to give you a little bit of help on the most important parts of this quiz, parts connected to what we had to miss. So this would be, looks like 4, 5, 6, and 7. I'll do those. The rest of them were from other classes. We don't have a lot of time, and of course this won't be the norm, but so to look at number 4 and 5, what you'd be thinking of, and this is just a quick review, you'd be thinking of what a reaction energy profile looks like. I'm not going to bother to label all the axes or anything like this, but your reactants start out at some energy, and then they have to bump hard, and then when you all the way down to products, that's the energy level of the products all put together. So that's the kind of question that goes, graph that goes along with 4 and 5. So a catalyst, what does a catalyst do to a free energy? Well, as opposed to the rate. The free energy change is here to here. So that is what we're talking about. That's free energy change, and what does a catalyst do to it? Nothing. Nothing. Absolutely nothing. What does it do to the free energy change? It does not change. That difference doesn't change at all. Now, a catalyst will do something. If you put a catalyst into the picture, and I'm going to switch colors for this one, you'll start out at the same place, and you'll do something like this, ending in, if I draw this right, exactly the same spot. All right, the catalyst doesn't do anything to where you start or where you end, but it does change something in the middle. And it changes the height of this hill right here. So in the presence of the catalyst, it does this. It increases rate, and it does that by lowering, you don't have to add this to your copy if you don't want to, by lowering the activation energy. I assume you've seen this kind of thing before. So this one should be that the catalyst increases the rate. A there. Anybody had anything different so far as you looked at your own copies? Okay. All right. The next question is about hemoglobin versus myoglobin, and if you remember the profile from the class session, I hope you remember something that looks kind of like this. And again, I'm not labeling axes on purpose, but one of these is the behavior of myoglobin, and one of them is hemoglobin. This top one is myoglobin, and this one is hemoglobin here. You want your storage protein, if it's given the job of grab the oxygen and hang on to it until it's needed, you don't want it to be prone to giving it up to the first hemoglobin molecule that floats past. Okay, if you come up with a storage protein, it should be myoglobin. So at low concentrations of oxygen, which one has the higher affinity? That should be myoglobin, by design and by function. It is better at snagging oxygen and holding on to it. Okay, the Bohr effect is the last question of this little group right here. Hemoglobin's affinity for oxygen decreases, meaning it wants to dump, it dumps oxygen. That's its job out in the tissues. You don't want it to hang on hard once it gets out where the oxygen is needed. It decreases in response to what? Anybody have an answer to suggest? There's more than one way to say this right. Yep, you could say lower pH. You could say higher concentration, molar concentration of protons, and that's fortunate because that's where the pH starts to tip out in the tissues as carbon dioxide builds up in metabolism. Okay, so were most of you on track with those? Most of you on track with most of them. All right. Well, that's what you need to be good then for this one. All right, so let's shift to the new things. You can hand those quizzes in at the end of class. And we'll try to stay on schedule here. We started talking about enzymes, so the quiz questions were for them. And this is the details about how enzymes function. Now, you've heard about them at least all of your academic career. And this is more of a biochemical approach that will hopefully give you some language to use and a little more precision, some background for standardized exams, should you ever have them. And there's a pretty standard abbreviation. For the substrate is the term that we use for whatever compound you're looking at that's going to be a reactant in the reaction that gets catalyzed. The enzyme is going to be a catalyst, and that's what a biological catalyst is called. Okay, so the substrate, we say it has to do something. Here's the reaction. The first step is something that forms a complex. Now, as of this stage, there's no reaction yet. These two come together, so the enzyme, of course, is a protein. This is a reactant, which may itself be another protein. It may or may not be. And here's this double arrow drawn here, and it has a meaning, which means that this thing right here, this first step, is really easy to reverse. The binding is extremely weak. No reaction yet. This is just the first step that's required. And there's another thing to know about even this first step. It's not random. Even though it's weak, it's not random. It takes place at a precise point probably on the surface of the protein. It's one place. I say one place. There are some enzymes that have multiple active sites, but it's still a precise place. And this is going to be on the enzyme molecule itself. It may be something like a groove, or it may be a pocket. That's an especially good fit for your substrate molecule. Enzymes are, you might think of them as good hosts. Their substrates are house guests, and they've arranged the furniture exactly to fit the preferences of their house guests. So there's some reasons why it's so specific. And by the way, the specificity is the secret that makes enzymes so good at what they do. This makes enzymes effective as catalysts. Maybe one of the first catalysts you would have dealt with in an organic chemistry class is sulfuric acid. That is not selective. That's cheap, brute force, destructive of as many things as it helps. Okay, not so with enzymes. Sit there, room temperature, pressure, quietly, selectively doing their jobs, turning out reactions so fast you can't keep track of them. Much better than sulfuric acid, and here's why. They've got these R groups right at the right spot. So I'm just going to do a rough sketch of what that might look like. Let's say we have the N terminal of a protein over here, and it kind of winds around to the C terminal. This is going to be a really general view. So here's the chain of the enzyme going along like that. No amide bond draws, nothing like that. R groups. And let's say that one of them looks like this. This would be serine. CH2, and I'm really going to emphasize that OH. And here's another one over here. This one would be valine. And there are others in there. Let's just pick out a couple as examples of what's meant by an R group and what it can do for a reaction. Okay, so the first thing you ought to kind of pick out about this spot in your R groups, and let's say this is in the active site, this is something that can form, you tell me, what kind of hydrogen bonds with the substrate. So just eyeball it. It's an alcohol. What kind of hydrogen bonds would you expect between this spot and your substrate? Hint. Lone pairs on oxygen, hydrogen sitting on oxygen. Looks like a recipe for a hydrogen bond, yeah. Okay, and here's another spot. All of that looks like something really greasy, really hydrophobic. So this spot right here can do hydrophobic. Bonds to the substrate. So there's two different examples. Any kind of force we've talked about before, it can happen. Except now it's going to happen between the R group that's dangling out of this enzyme and the substrate. So we're talking about a bond between an extremely big molecule, the enzyme, and potentially a very little one. That's what a lot of the metabolic reactions look like. So that's one reason you've got specific binding. It will do only certain things in only certain spots. And then there's this bit about 3 dimensions as best. It goes, this specificity, this route to being specific, is something you talk about. It's going to work best if your substrate is chiral. That means either R or S. Now that's absolute configuration, not the substrate molecule. Sorry, S means 2 different things, doesn't it? In organic it means not R, and in biochem it means the substrate. So it works best if your substrate is chiral. If that's the case, you're looking at a fit that's extremely good. And the fit we care about is the fit between the enzyme and the substrate. There are some enzymes that will discriminate between the R and the S enantiomer. And that's better than just about any synthetic organic catalyst will do. And this, again, is a natural molecule. Oh, sorry. I think I better toggle out a little bit. This font is bigger than the quiz, so maybe we don't need it to show quite so much. Okay, and then there's one thing that you will never find with sulfuric acid as a catalyst, which is that you put the 2 of these together, the substrate and the enzyme, and they end up being a better combination than either one was separately. So the enzyme plus substrate are going to fit even better after the substrate binds. Show me any non-biological catalyst that works that well. That is awesome. The 2 of them come together and bind, and then the catalyst rearranges itself so it's even better. All right, that's 3 reasons that substrates or that enzymes are in a league by themselves as catalysts. Okay, so let's move ahead and think about the next step. All right, here's where the actual chemistry starts, at least in the sense that you would have thought of a reaction in organic chemistry. Now, again, it's run as reversible. So let's say, yeah, some of them are, some of them aren't, but many of them are. Many of them are reversible. And look what you're starting with. The complex itself is already there, and we assume that it's good enough to have lasted this long. When this step is all over, you're back now to free enzyme. It's available to find another substrate molecule and go do the whole thing all over again. Here's the product molecule. And what that means is you've got no more substrate. At least as of the end of that step, the substrate has been destroyed in the sense that it's been converted into something else. Now, in this step, we're talking about how the enzymes helps with a reaction. And let me just remind you the difference between that and where we just were on the other page. Binding, that's even before the reaction happens, okay? This is before the reaction itself. Whereas what we're talking about on the second page is in the chemistry itself. Okay, so you can kind of number these. Here's the first one. The orientation of the substrate sure is a lot better thanks to the R groups, and remember, these are the ones that are right in the active site of the enzyme. So the substrate is probably sitting better to perform the actual reaction, let alone where it was to begin with. Then, of course, there's the energy of the transition state, which gets lowered by R groups in the right places. Probably what you want to do is think of this is they stabilize the transition state. So it does not have to get kicked up to as high a hill in that little potential energy diagram that I kind of started the class with. And then there's this business of catalysis that's kind of like what you've seen in an organic class. Acid bases and bases look like, well, just one of two things. So nature hands you a set of characters that can be either way. Some of your R groups can behave like an acid. And so that would be something like this R group. There's one called aspartic acid that looks like that. That is a flat-out proton donor. And there it is as a functional group that you had in your first organic class. And now here it is as part of a bigger molecule, an organic molecule that's functioning as a catalyst. And then there are some that can function as bases as well. There's lysine, and it's got more spacers than that other one did. But if it were in its basic form, that's what it would look like. It would be a base, and now you're often going into the game of just shunting protons around. And you know, how many of you remember any organic reactions at all? Right? Do you remember drawing a few curved arrows? Isn't it almost always the case that you're adding a proton or taking a proton away from something? Okay, same thing here, except that you're going to blame the source of the proton in this reaction on this one amino acid R group at the right spot, the perfect spot in the protein molecule, the protein being the enzyme. And there's a base that can do the same kind of thing. So that would be kind of your third set of reasons why enzymes are a good catalyst. There is another family of reasons, which is sometimes there can be a metal that's actually involved. And let's see, what would be an example here? Magnesium gets involved in a lot of catalysis. Mg2+, which is, I don't know if this is a technical term, but recruited by the enzyme. It may be there to begin with, stuck to the enzyme, or the magnesium may get recruited in the reaction itself. But sakes alive, these proteins, the enzyme molecules, are big enough, and they've got enough different groups on them that they can be reaching out and kind of grabbing what they need to make this happen. And then there can even be something that we call covalent catalysis, which is what it sounds like. There will be covalent bonds broken and formed. So this, just in a brief abbreviated form, would look something like this. You'd have an enzyme, and one of the most prominent covalent interactions we looked at within a protein would be an enzyme. So let's say that there's an enzyme that's linked like that, and so you may have this, that actually looks like sulfur, doesn't it? This is supposed to be substrate. Great, we've hit two different ambiguous abbreviations today. S can be substrate, sulfur, or absolute configuration. Okay, only a group in a university level biochemistry class would have seen all of those in the same setting and kind of know how to keep them straight. So you know where you're at here. So of course that spot right there is the covalent one. And let me just make sure. In this case, we're looking at a disulfur bond. And the sentence is talking about substrate. I realize that that's several S's to keep separate. Okay, but the bottom line is this part of the enzyme can break and reform bonds to the substrate. I'm going to spell out that whole word so we're not getting more confusion around that letter S. There's a list for it. How many is that? That's 5, it looks like. Reasons why enzymes are good at what they do. Hold things in the right place, lower the transition state energy so that it's easier to do, shunt protons around, provide metal ions as catalysts, and even get involved with making and breaking covalent bonds. Sulfuric acid, blunt, dangerous catalyst that it is, used in sophomore organic chemistry, you couldn't say anything about it except for this one thing here. It knows how to donate protons, and after it's done that, it's done. Nothing this sophisticated, and certainly not at the awesomely mild conditions that enzymes operate at. Body temperature, neutral pH, everything nice and gentle, and they're off and going. Okay, now enzymes are they're not as brutal and they're not as robust as sulfuric acid. That's their downside. So there are a number of things that you can do to damage them, and it turns out that anything that affects enzyme folding, which would be really tertiary structure, that's the main death of an enzyme's function. If they get folded wrong, you need to stand back and let them refold, or either that or edit them, dispose of them, and start with a fresh molecule. But the main things to blame are a temperature that's too high or too low, a pH that's too high or too low, and organic solvents. And that should be a familiar list, because what all of these do is, let's see if you remember the word. I thought I heard it. Yeah. Denature. You mess up this beautiful three-dimensional structure that the protein, the enzyme molecule, has to have, and it doesn't work anymore. No surprise there. So like were most of you here when I scrambled the egg with ethanol? Okay, you would scramble an enzyme molecule if you dunked it in high concentration of organic solvent. Get the pH too high or too low, get them too hot, it's all over. You may have heard how many of you have had a physiology class? Okay, how about A and P? Automatic physiology. Did you talk about heat shock proteins at all? There's some proteins your body makes specifically in response to temperature that's too high. And their job is to go around and start checking and protecting the critical proteins in the cell. Specifically, they're called that because they're made in response to heat shock. All in an attempt to protect everybody else. Of course, there are buffers both inside all your cells and circulating. That's an attempt to keep the pH at about the right range. Organic solvents, just don't go drinking them, okay? That's your main protection against it. All right, so that's the way they function, and we're going to put a mathematical model on this and be able to say something precise about reaction rates. This is a toned-down version of what your textbook does. It's all we really need in this class, so yeah, the textbook is good for some things, but not the exact version we're going through here. All right, Michaelis Menten, that's just the name. You don't have to remember that. But it's the only one, it's the only model of enzyme kinetics that we'll be looking at in this class. And remember, enzyme kinetics, this is not looking at reaction energy, it's looking at reaction rate. So this is how fast a reaction goes. Now we'll talk about some unit for that. It will need to be something per unit of time. All right, we're looking at understanding the rates of some enzyme catalyzed reactions, and there are two practical uses for it. One of them is it'll help you learn a little bit about the actual enzyme mechanism, meaning things like the order of bond breaking and forming. That's one thing. And then the big practical reason is that if you understand the kinetics of an enzyme, you can start to talk about how to regulate it. One of the main categories of drugs out there as a group is called enzyme inhibitors. Now that's as opposed to things like beta blockers. Do any of you have a family member who's taking a beta blocker or a COX inhibitor or something like that? That's to prevent inflammation. Drugs get categorized by mechanisms. One whole category of drugs is regulate an enzyme. You may want to slow it down or speed it up. If it's a mutant in a malignant cell, your dream would be to find one enzyme in that one cell and find a way to shut down it only. Usually drugs aren't that selective, but that's kind of the notion. All right, that's the reason people do this kind of thing, and that's your dream. So here's the model, and you have seen this before. We just went through this. This is step one. It gets you to a complex. And here's step two. It gets you from the complex to product. And here's the reactant starting out. All right, and there are other options out there, but we're going to ignore them and assume that this is the only thing we have to worry about, what you've already seen. All right, so what I want to do first of all is kind of tell you what you don't need to do. Here's an equation. It's the only one we'll be using, and the first thing I'll ask is don't memorize it. If you need to use this on an exam, it will be given to you, either printed on the exam or written on the board or something like that. So we will concentrate on interpreting it. And yeah, let me just start and go kind of from left to right here. V0. What is that? Well, V in this case stands for velocity. It's how fast something goes. In this case, it's the reaction, how fast it goes. Okay, I think that's big enough to see. How fast the reaction goes. And this is at a specific time. When the enzyme and the substrate are first combined. Any reaction is going to kind of lose juice and slow down after you start running out of substrate. So that's not when you go measuring this velocity. This is when the enzyme is at its best, when it's got plenty of substrate around so that you can see it performing like the awesome catalyst that it is. Okay, now remember that all of this put together, this V0 right here, V0 is a variable. So it's going to change depending on how other these things get mapped in. It could be in units of moles per second, or it could be units of maybe millimoles per second. That's millimoles of product formed. All right, this is like the speedometer for the reaction, and you have to have some way to observe it. We'll assume that that's done for you. Okay, then we'll kind of take these two right here as a chunk. Vmax and Km. All right, what are they? These are not variables. These are two constants. And they must be measured. Either measured or given to you. And then we're back to something you recognize. S in brackets. Now that just means the molar concentration of substrate. This is variable. Okay, so that's the equation itself, and what we're going to be heading for is interpreting this and using it. So maybe more detail than you really need would be kind of thinking about this over here. Got some space to label this, so let's think about this. There's that S in brackets. Now what you'll be wanting to notice is it shows up in both the top and the bottom of the equation. If you're thinking in words, that's a way of saying, well, substrate is both good for velocity and bad. Okay, and we'll get to how that works. But what it is, let's define this. It's concentration, meaning you've got a solution. It's concentration of substrate. It can be in units. There's more than one option of either maybe moles or micromolar or even nanomolar, just something that's consistent. I trust you remember that molar is moles per liter. That's just kind of thrown in free there as a reminder. All right, it's a concentration, and it's of the reactant itself. You know this because you set up the concentration, you weighed out a certain mass and dissolved it in a known volume. So that much is just like freshman chemistry. Make up a solution. Okay, now the next one, Vmax. Let's get into interpreting that. And it kind of sounds like what it actually is. This is going to be max. In other words, it's going to be the highest initial rate that this reaction can ever have. Vmax. That's for this enzyme, for this substrate, all of these conditions, best you can ever have. Now you'd have some units here, and it looks like it's going to be awkward units, and it is. So if you did this, what you'd find is it's going to be concentration. Units are concentration divided by time. So it could be something like moles per second, or it could be millimoles per second. Whatever it is, some change in concentration per time that sounds like a reaction is happening, and you're tracking how long it takes to happen. And then the last parameter in this equation is Km. That's the so-called Michaelis constant. And it is one, I'm going to spell this all out here, it's one specific substrate concentration. Oh goodness. Don't we already have substrate concentration in there 2 times already? Yes, we do. But those are variables, and this one is not a variable. This one is hardwired into the enzyme. Okay, this one isn't a variable. It's one specific substrate concentration, and it's picked out because of one thing. It causes the initial velocity to be exactly 1/2 of Vmax. That's the substrate you have to get to in order to get the reaction going half speed. Okay, a little bit more interpretation. Let's interpret a few things here. One thing you're looking for if you're a drug designer is the difference between a low Km and a high Km enzyme. So let's think about that. A low Km means that the enzyme has really high affinity for the substrate. And let's think about this in another way. It doesn't take much. Okay, that's an awesome enzyme. If it gets off and going half as fast as it ever will, and you've only had to add a little bit of substrate, it's like saying the accelerator pedal on your car hardly has to be tapped at all, and you're off and going. 0 to 60 very, very quickly. So that's what a low Km would mean, and of course a high Km means the opposite. I won't clutter that up by saying this that much. Another thing to interpret would be Vmax. Let's put maybe one interpretation statement on that. If Vmax is higher, here's what it means. It means that your enzyme is faster maybe than another enzyme at catalyzing this reaction. Okay, now those are the 2 constants, and let me just emphasize that. Here's how you interpret those constants. Now, substrate, you just make up different concentrations of your substrate, and that's why S has brackets around it. It can be anything. These other numbers right here are much more specific. And I guess I just took that off the zone where you can see, right? Okay, are there questions about that? Okay, here's where I'm going to depart majorly from the book. The book, there is a way to figure out Km and Vmax with a formula. Okay, I understand that. But you have to use an Excel spreadsheet, and you have to plot, do what's called a double reciprocal plot. If you were in the 2-semester sequence of biochem, I think it would be worth doing. For us, it's something we need to look at and grasp the concept within 1 day. That's the scale we have. So here's the graphical version of this equation that we just kind of interpreted on the other page. And here's a standard plot. I want to kind of fill up a good-sized chunk of the page with a plot. So here's what you're looking at. Your variable is the substrate concentration, and what you're observing, the dependent variable, is the initial velocity. This will be in units of something like moles per second or millimoles per second. Can be any concentration. And down here your substrate concentration will be moles per liter. It can be millimoles per liter, just some concentration. So you throw various concentrations of substrate at your enzyme and say, okay, how fast are you going to work if I give you this amount to eat? You'll see a curve that will look something like that. It goes up kind of fast and then it levels out. Okay, up here it looks like there's a ceiling that this thing has hit and it doesn't want to go any farther. And what do you suppose you call that? Now let me put up the different variables again. This is the best this enzyme is ever going to do, so what do you suppose you call that from this equation? Yeah, never will get better. So right there, that spot is Vmax. And notice it has units of moles per second. It's a velocity. Okay, and then we had this little formula that said, well, look for the substrate concentration that will give you half that reaction velocity. So, like right there, that's Vmax, half as good as it's ever going to get. And so you're saying, well, what substrate concentration does it take to get this thing going half as fast as it ever will? And to look at that, you just run a line across from Vmax over 2, and then you drop down and say, okay, where does that land me on this scale right here? And there's the number you interpret, because at that point you're looking at Km. Km, and remember this interpretation, which is a substrate concentration, and it's the substrate concentration that makes this enzyme go half as fast as it ever will. Oh, words something like this. Work at 1/2 of Vmax. Okay, how are we doing on time here? I think we've got time for an example problem that's in one of your homeworks. So let me do that and call it done. So here's how to use the numbers. Using this thing graphically is a way of saying, if you can look at this plot and eyeball the numbers, we'll just say that's the way we do it in this class. We're not going to have you plot two reciprocal pieces of data against each other and calculate it by algebra. So I'll work through an example of how we'll do this. If you can draw lines about that straight, and, well, okay, maybe a little straighter than that, but, okay, be able to differentiate something that's here from something that's here or here. That's what we're headed for. And also get your units right. Okay, so what we're going to say is, what we're given here is Vmax, and this is going to be what you want to calculate and let's say that you want to calculate that for a substrate concentration of 2.38 micromoles per second, and let's say that you're given this. Let's say that you're given that Km is equal to 5.35, and again, watch your units, micromolar. You're also given that the substrate concentration is equal to 3.65 micromolar. And let's have you calculate V0. I'm going to change this, not want, it's what you need to calculate for a substrate concentration. And Vmax, we're going to say, we're going to define this as 2.38 micromolar per second. Okay, so there's some numbers, and here's how you do a calculation. You go V0, and you're going to plug and chug here. Vmax times the substrate concentration all over, and this is where I see the confusion start to come in sometimes. You multiply by substrate in the top, and you only add it in the bottom. If there's any one pitfall to using this equation, that's where it usually comes in. Okay, so you drop in the numbers, and let me see if I can leave enough space to label these. So in goes the 2.38 micromoles per second. There's one substitution. Here comes the next one, 3.65 micromolar, and then you're going to divide through, and don't forget there had better be an addition in the bottom. 5.35 micromoles. And here's what I'll emphasize with a plus sign. There's that, which is easy to forget. 3.65 micromolar. Okay, all of that, by my calculator, comes out to be 0.965. And there had better be units that are velocity on it. So don't get your units mixed up here. Micromolar per second. Okay, here's just real quick Vmax. There's a substrate concentration. Here's Km. Here's a substrate concentration again. So the kind of the word interpretation you put on it would be something like this. At this substrate and this Vmax, there's a certain amount of substrate available, and the enzyme is capable of only delivering so much. And Km, all of that put together, the initial rate of this reaction is 0.965 micromolar per second. And we had better be done right there. End of time for the day. Yeah. Okay, quizzes are due here. I think that's the only item of business. Other than that, so this,
for some of those you said micromolar but wrote micromole. Which is it?
yeah, let me put that in. Micromolar.
Okay.
Sorry, that's too little to be used.
And the answer is that one micromoles per second or micromolar per second?
Micromolar. Yes. So I got in a hurry there. Okay, see you next time, and we'll be done with what, 3 weeks?